to her whether she wants to put it in the class website or not. But anyway, so I'm just going to stop for her for today. And the topic that I'm trying to focus for today is polyatomic ion, or diatomic ion, diatomic molecules, maybe. And specifically, some heterogeneous ones. So far you've already done, for example, N3 or nitrogen molecules, O2, and so on, which is both atoms are exactly the same. And what you've done so far is essentially, if you have things like nitrogen, you have, for example, you have 3 2p orbitals and 1 2s orbitals. And I'm going to eliminate the 1s because we don't really care about it, because they're so deep inside the nucleus, more or less, it's not contributing too much in the bonding. So if I were to have nitrogen, each of the nitrogen have 5 valence electrons. So the number of electrons initially, before a chemical reaction happened, looks more or less like that. Right? So this is before a chemical reaction, but once you have a chemical reaction, you have a molecular orbital diagram. So these are just your, if you simply look at your periodic table, you have 1s, 2s, 2, 2p6, and so on. This is all we did. And this is before. And then once you have a chemical bond, the chemical bond, when it happens, you're going to try to mix now these two electrons together to make a molecular orbital. You can have, there should be symmetrical, but I'm just being sloppy right now. So you have a bonding in the s orbital, and then you have a sigma bonding orbital. You have pi, 2 pi bonds, right? And is it like this, or is it like that? So which is the proper energy state? This one? Okay. Double checking. Double checking. So this is what we want. So the new, whatever that we have here in the middle, is what we call as, or usually referred to as the MO diagram, or the molecular orbital diagram. And we're not calling it atomic orbital because now we have a molecule. We have 2 molecules bonded together. So instead of atomic orbital, which is what was before, we have molecular orbitals. But the idea remains the same. So if you remember your Hess's law, your Pauli principles, and so on, it's the same thing. Your electron is just going to try to go down as low as energy as possible. So it's going to fill in all the way to the bottom from the top. So in the end, each of the molecule have 5 valence electrons. So we have 2 of them. So we have 10 valence electrons in total. So I'm just going to count 1, 2, 3, 4. Whoops, it's not showing up. 5, 6, 7, 8, 9, 10. So this is what we have. Right, it's just kind of, we're just filling all the way from the bottom to the top. I am being sloppy, this energy should be lower than the energy of the 2p orbitals, and certainly I'm being really sloppy just because I'm not used to this room. There's no podium. Usually I write it down marginally better just because it's a bit more comfortable. Let's see. A little bit of review. Is this a paramagnetic or diamagnetic molecule? Okay, so this is diamagnetic. And what is the definition of diamagnetic? No unpaired. There's no unpaired electron, that's why it's diamagnetic. But the definition of diamagnetic is that they repel magnetic field. Okay, so let's see. The next one will be just kind of a bit of a review as well, just make sure that we're on the same track. We have, in this case, what is the bond order of this particular molecule? So you know the answer is supposed to be 3 because nitrogen and 2 have 3 bonds, have a triple bond. But how do you calculate for the bond order? Sure. So you have bonding electrons minus anti-bonding electrons divided by 2. So if we look at the bonding electrons, we have 2, 3, 4, 5, 6, 7, 8 minus anti-bonding orbital, which is that one, 2 divided by 2. So we have 6 divided by 2, so we have 3. The bond order is 3, which is exactly what you expect to see when you draw a nitrogen molecule. We have a triple bond and a lone pair at the end. Alright, so that's your general Lewis diagram. And in the end, your bonding, I forgot what the O stands for now. Anyway, the bond number is 3. Bond order, there you go. Catching my... I'm switching around between quant and this class, so now my brain is still switched from quant. Anyway, let's see. The next one that I want to cover, we'll just kind of wrap everything up together. We're just going to try to draw all the possible drawing state of these states that we have. So initially we have, on the lowest state, we have a sigma bond between the s orbital and another s orbital. And usually, the way that we draw the sigma bond is we simply have an s orbital and we overlap it again with another s orbital. Right? And I'm using the same shading here. So essentially, once you have the same phase, it's like two waves undulating together, the wave gets bigger. So the picture that we have is something that like that. Okay. So literally now there's a lot more electron density in the middle between the two atoms. So that's really the picture of the bonds that we have. We can also have a sigma anti-bonding orbital between the two s orbital. And usually we give it a name for the star. And essentially the two s orbitals are now different phase. And I'm just going to show the different phase just by shading it differently. Because usually you don't have two-tone pen all the time, so we're just going to shade it. So what happens when you have two orbitals that overlaps but they have different phase? What would happen to them? The wave would cancel. That's exactly right. And essentially this is a constructive interference. Did you guys use the term constructive interference or no? No? Okay. I guess I see a lot more shaking, so I just assume no. So the best way to think about it is that the lighter shade one is +1. So +1 and +1, you add it up together, it becomes +2. But if you have one of them is +1, the other one is -1, they cancel out. And they cancel out specifically exactly here in the middle where they meet. So what happens is that in the middle between the two atoms, you have what they called a node. You use nodes, right? Yes. So essentially, because right here, exactly where they meet, there is a node. You create a node. And essentially, you're just quite literally in an anti-bonding orbital, you have no electrons between the atoms. So you have a node here in between. You have a node in the anti-bonding, and you have no electrons in between. Hence they're called an anti-bonding orbital. There's literally once they have the phases are not matching up together, the probability of finding electrons between these two atoms is 0. So you have an anti-bonding orbital, they literally just fall apart. And essentially when you want to break a bond, it really doesn't matter what bond it is, you're going to put essentially one of the steps that you do, you put everything in the anti-bonding orbital. So this is what we have. We have a sigma bond between the two. We also have, for the two p orbitals, we have one pi bond between the p orbitals, as well as one sigma bond between the p orbitals, as well as 2 pi bonds between the p orbitals. So this is a sigma bond between p and p orbital. And the picture that we have is that when you have a p orbital, it looks like a dumbbell. So as always, the bonding orbital is going to overlap exactly the same phase. So in the end now, between the two atoms, we have a agglomeration of electrons. Hence, you have a chemical bond. So it's just, this is an acceptable drawing, but the actual thing is that once they have the same phase, they actually merge together. You guys seen this before? Yeah? Okay. You're already familiar with it? You're fine? Okay. So we'll just do the p orbitals, and then the antibonding is just the reverse. So you have two different kinds of pi bond. You can have a pi bond between the two molecules like this, which is in the z-axis, and you also have a second pi bond in the y-axis. Sorry, my dumbbell looks squishy there. So you have two of these things, they're two distinct bonds, and that's your two pi bonds. And again, they're in the same phase, that's why the orbitals overlap, and you have a chemical bond. And I'm not going to show the anti-bonding orbital because you simply switch the phases around. And I think your textbook also has a picture of what it actually looks like. So that's kind of more or less kind of the review. My question is, can you distinguish whether something is a pi bond or something is a sigma bond? Did you guys cover that already or not? No. So if I were to have a chemical bond that looks like this. So this is a p orbital, and this is an s orbital. Would you call this a sigma bond or a pi bond? This is a sigma bond. We can also have a variety of different kinds of sigma bond. You can have a sigma bond between s orbitals and the d orbital, because you have d orbitals. So this is also a sigma bond between s orbitals and d orbital. Essentially, whenever you have a direct overlap like this is called a sigma bond. And obviously, you can also have sigma bond between p orbitals and d orbitals, and so on and so forth. Now, the reason why it's called sigma bond because the first sigma bond possible is in the s orbital, so it starts with s for sigma. So in this case, but you can have sigma bonds with a bunch of other orbitals as well. So this is a sigma bond between p orbitals and d orbitals. The next one is the one that you've already seen before, is a pi bond. And obviously, if I were to have something that looks like this is a pi bond between p and p orbital. And I can also have a pi bond between p and d, or p and f, and so on and so forth. So for example, if I were to have a pi bond between p and d orbital, it might look something like this. And what I wanted to notice for now is just kind of how they actually bind. And it's a pi bond is kind of a somewhat indirect overlap of the orbitals. And it's called pi bond because you have two p orbitals. Is the first pi bond possible? So how about a bond that looks like this? Oh, it's going to be such a hassle to draw. What would you call this bond where your overlap is between these two lobes, these two, and the one on the back? So you have two d orbitals back to back, essentially. I'm trying to draw it, but I'm obviously having a hard time drawing it. So you have two d orbitals back to back, and the lobes are overlapping like this, like a sandwich, exactly. How would you call this name? Sigma bond? Pi bond? No, not a pi bond. This is p orbital, pi bond. Delta bond. This is the delta bond. That's my delta bond. And essentially, you just go alphabetically. I think F is a femto, and F orbital has like 6 flower petals instead of 4, and so on. So this is kind of some of the names. So you have sigma bond, pi bonds, and delta bond. Sorry? This is not a triple bond. This is still a single bond. This is still a single bond because you have one orbital and one orbital, so it's still just one bond. It's not a triple bond. It's called the delta bond. That's all. It's just how it overlaps. So, which of these? How would you draw a pi star d and d orbital? How would you draw a pi star orbital, so an anti-bonding orbital between two d orbitals? Yeah. So that's your two butterflies side by side instead of sandwiching. But now your phase must be in opposite. So one of them is that way, and the other one is that way. So now you have these two are minus 1 and plus 1 again. Right, so your phase are not the same anymore. So now you have, because they're overlapping in opposite phase, exactly in the middle, they cancel. The probability finding the electrons in between the two things is exactly 0, hence anti-bonding orbital. So I think once you get the picture, once you draw it, it's actually pretty straightforward to distinguish whether something is pi bond or sigma bond and so on. The next one that Dr. Probisco wants me to do is go into a diatomic molecule where the molecules are different from one another. But actually, before we go there, there's one thing that I forgot that she wanted me to ask. It's just a bit of a definition. If we were to have, so if we have the nitrogen molecule that we had before, the the molecular orbital diagram looks more or less. I really need to do this a little bit better. Sorry, I'm being sloppy with my drawing here. The terminology that Dr. Probisco wants me to cover is LUMO and HOMO. I should put the LUMO. You guys haven't covered this one, right? No. So this is just a couple of definitions. So we'll do the one on the bottom first. The HOMO is an acronym for highest occupied molecular orbital, and the LUMO is the lowest unoccupied molecular orbital. Now, majority of the time, the name should be fairly straightforward. So, if I were to have this nitrogen N2 molecule, which one is my HOMO, and can you describe it for me based on the pi bond or the sigma bond, or sigma anti-bonding, or whatever? So, let's say this is A, B, C, and D. HOMO is D, and LUMO is going to be E. Okay? So, sorry, I forgot E and F. So, highest occupied molecular orbital. Forget about the molecular orbital. So the highest occupied is here. So the highest occupied molecular orbital is right on the top, and specifically in this particular molecule is the pi bond between the p and p orbitals, and the LUMO is the lowest unoccupied. So it's whatever else that's empty, which is that one. In this case, it's the sigma antibonding between two p orbitals. Yeah. So the lowest unoccupied molecular orbital, just a little bit of definition. So this is the lowest unoccupied because it's empty. So it's called the LUMO. And then we have the highest occupied, which is the HOMO. And of course, if you have different molecules, you can have a different arrangement of the HOMO and LUMO as well. So if you have, instead of N2, you have oxygen gas, you'll fill in the second lowest energy tier. So it just tells you which one is the empty one and which one is the lowest one. Majority of the time, that's kind of the one that you're interested in, because if your molecule will then kind of absorb light or undergo some kind of absorptions or emission process, you're either going to have to go to whatever unoccupied orbital first. So, for example, what I meant by that is that if this particular molecule, so nitrogen gas, is absorbing some kind of light, then the absorbent must go from this state to some kind of an empty state. So you can go from here to there, or from here to up there, or from here to there, up there, and so on. And usually you kind of call these things, on occasion, people do refer it as LUMO 1, LUMO 2, and so on. So this is LUMO 2, LUMO 1, HOMO 1, HOMO 2, and so on as you go down to the bottom. It's just kind of a labeling mechanism, and sometimes people just put an acronym that the LUMO is this and so on. So it's a bit of good terminology to master and just get used to it. But otherwise, it's not too terribly difficult to remember. So we have definitions, and we have that, and you guys are familiar with the drawing, and I don't think there was any particular issue with distinguishing the bonds. Now, the next thing that I want to go to, any questions so far in terms of definitions, the shapes of the orbitals? Yeah. Yeah. Right. How much math do I want to get in there? So let's do. Can you define the question again? Sorry. What do you mean by the
two anti-bonding d orbitals?
Yeah.
You showed how they would align, but you didn't show how they would actually
deform. Yeah. So if you have a d anti-bonding orbital, so we have a nice d orbital that looks. What it is that my drawing is already deformed. So we have two d orbitals that looks more or less like that. And if we were to have an anti-bonding orbitals between these two things, they have opposite phase, they will have an interaction right here when they meet, and they will deform. The actual deformation would look something like this, that it's just wherever they meet here is going to be 0. So just kind of think of there's a dividing line where there's probability of finding an electron is 0. And essentially the lobes get shrunk a bit. So now instead of an equally distributed butterfly, you have a molecule that looks something like that. Now, remember, the drawing that I'm making here is the probability of finding the electron. Since we've already eliminated the probability of finding the electrons here, in fact, this lobe here gets bigger because the probability must be equal to 100%. I'm simply moving from one side to the next one. So this lobe actually gets slightly bigger as you go as well. So you can have a picture that looks like that. So this is the actual distorted.
So we wouldn't necessarily have a repulsion from the two air lobes. We would have, we just have an increase of probability. Right?
Both? Well, the repulsion is that you have none in between.
Right, because I mean, if you're looking at two s orbitals, they're
Right.
two spherical, right? But then when you get to anti-bonding s orbitals, they become more elliptical to the out.
Right. So you're talking.
I mean, So you're saying in d orbital they don't really.
No, it's
get data on that?
well, yes, but it's the same kind of distortion. So my size here, if this is the p orbital, so this is my resulting orbitals is you have like a distortion there. It's the same distortion that's happening. That is, if I were to try to overlap what it looks like in the end, then I have none in the middle here. So the probability density simply shifts that way a bit more. So same thing with this one. That is, the probability density shifted that way. So now we have this lopsided. So I probably shouldn't choose the light blue. They have the same thing. So same with this one here. So the probability here gets truncated, and it's simply whatever probability that we're missing on the side get bounced out to the outer side. So in fact, they do kind of increase. And I'm drawing this as just exaggerated, but the actual increase in changes is actually not that big. This is just an extreme exaggeration, so it shows up better.
Do you have a marker or?
Yeah, just draw it here. Just draw it here.
So I would have thought like, not exactly.
Yeah.
So you'd have this one, and you have this one like deforming into that side because it's getting it's getting repelled from this one.
They're not actually repelled. And the answer is yes, they kind of look close, but not like that. It doesn't actually get repelled. It's
Right.
simply the probability disappears.
That's what I thought it was.
Like
Repulsion.
an eraser rather than like an actual repulsion.
Okay.
It's like erasing.
So it's not repulsion.
No, it's not repulsion. There is a natural repulsion between the two electrons in there, but it's something else. But it's not a repulsion. It's literally it disappears in the middle. Yeah.
Maybe I could help a little bit.
Yeah.
I don't know. I just think of it like it's sort of like wave functions, where we're trying to graph the wave function and not the
Right.
electrons. So the electrons
Right.
repel, but the wave function.
That's right.
So we're looking at how they like.
Yeah.
where the-
Which is wrong.
Right.
Did you guys go over? LCAO, linear combination atomic orbitals, or not yet? And so the picture that we have here, so if we go to the LCAO, or linear combination of atomic orbital, we can try to draw this mathematically too, but I'm just not sure how. Usually it's more like quantum mechanics class instead of advanced inorganics, so I'm not entirely sure how much I want to go into it, which is why I'm not trying to bring it in the first place. But essentially it's something like this. You have the wave function. Do I want to use wave function number 1? Right, so you have the do I want to go over here? I really don't. Well, why not? So if you have in this case, either an anti-bonding or bonding orbital, you ask, I don't know where to stop.
I was trying to understand.
Right. It really is basically like your algebra. It is really just algebra. So, right. So if you have a bonding orbital, it's basically your orbitals, two orbitals overlap and add up. And if you have an anti-bonding orbital, so this is bonding, anti, you have orbital 1 minus orbital 2. And so that's your anti-bonding orbital. That's why they subtract in the middle. So how do I find out? The graph that we're trying to draw here is probability of finding electrons. That's what we're drawing. So if I have a wave function, what do I have to do to find the probability of finding the electrons? Sorry? Yes. Yes, it is. Yes, it is. But the simplest thing that I want to mention is that you simply to the power of 2. Yeah, so you square it. So if you square this thing and just kind of assume that it's entirely pure algebraic equations, then I'm going to multiply, right? So this is going to be I'm trying to, right, so let me actually do it this way. And instead of kind of distinguishing A and B, let's just kind of collapse them together, just the wave function, right? Just the standard wave function. So if I were simply kind of square them together, I have the wave function squared plus 2, I do need A and B. So wave function A times wave function B plus wave function B to the power of 2. Yeah, so this is what we have. And we can do the same thing too. So this is wave function A squared minus 2 wave function A, wave function B, plus wave function B to the power of 2. So in this particular algebra, what is your actual chemical bond? In terms of algebra, your chemical bond section is just this portion here. This is your chemical bond, and your bonding orbital is this positive sign, and your anti-bonding orbital is that. You see, it's just it really is just probability. This is really once you go to mathematical terms, your chemical bond is just that. At least in terms of probability density, there is literally an increase of density in between the two atoms. So we can actually just kind of look at it based on number 2, which is, if we look at it, if I simply have, suppose that I have 2 orbitals that's really, really, really far apart. So if I have orbital 1, so this is wave function A, and I have wave function B, such that they're so far apart, then the probability density is just wave function A to the power of 2 and wave function B to the power of 2, right? So if they're further apart, the probability of finding them together is just, you have 2 electrons, one of them is on one side and the other one is on the other side. But once they get together, when they get closer, as you go closer and closer, then the bonding will start to emerge. In this case, 2A times 2B, right? It's really just that. But there's a few issues though, because once you have a bonding orbital happening, the sum is this, right? But did you guys go into normalization at all? Yes, right? Okay, so you went into normalization. So the wave function squared, suppose that the wave function squared is just 1, so it's 100% you have 1 electrons and 1 orbital. So this is 1, and this is 1. So wave function A squared is just 1, B squared is also 1, but now we have in the middle a cross term. Let's just say this is plus, it doesn't overlap entirely, but let's just say this overlap is 0.1, right? So now when you have a chemical bond, the sum is not just 2 electrons anymore. So if there's no overlap whatsoever, it's just wave function squared A, which is just 1, plus wave function squared B, which is also 1. So the sum is just 2. Sum equals to 2. But now since we have some overlap between the two, which could be tiny, it's actually most of the time very, very small. Now we have 2.1. You can see that now there's a slight change now in terms of our probability. So if I were to have 2 electrons, now that we have to normalize it, on one side we have 1 divided by 2.1, and we have 0.1 divided by 2.1 plus 1 divided by 2.1. Okay. Versus this is bonding, and no bond whatsoever is we have 1 divided by 2 plus 1 divided by 2, because there's no bond whatsoever. So what it simply means is that this number here, there's more in the middle where none exists before. And what I want you to notice that this number here goes down as well. This one gets smaller. It gets smaller by a tiny bit. Initially it was just 1 divided by 2 becomes 1 divided by 2.1. So when you have a bonding orbital, so this is probably will add up to your thing. In the bonding orbital, you have more electrons in the middle because it would be more than you would expect before the bond was before. And at the end side, on the outer edge, there's going to be less than what you expected to be before. Huh? Almost what? Yeah, because it's denser, more probability in the middle, then the probability from the outside shrunken. So it's, I suppose this is an accompanying to what you were saying before. If my initial orbital density looks like this, so if my orbital before a chemical bond happened looks like this, entirely spherically symmetrical from one side, the outer edge here gets shrunken a little bit as well. So they get sucked into the middle because it's all about probability density. It's a bit weird. Obviously, there's actual energetic term that you gain from doing this, because we actually haven't gone into the Bernoulli wavelength. Did you guys cover that at all? Yes, tiny bit. Yeah. So if your wavelength is big, is it lower energy or higher energy? Oh, yeah. So your wave initially looks like that, but now that's you make a bond, your wave literally gets bigger, so your energy goes down. Hence, when you have a 2s orbital, it goes down because the wave literally gets bigger. Whereas the sigma bond, the wave gets smaller because now instead of having 2 like this, so this is your original, this is your bond, your anti-bonding, your wave gets truncated, and remember your atom wave function expands all infinitum, although it's kind of around the atom, but now it used to extend all the way to infinity, but now because there's an anti-bonding orbital, your wave function literally gets cut in half. So now your wave function gets smaller, so the energy goes up. Same thing. It's all Gen Chem 1 except with fancier language. Now that I am entirely not on track of what I'm supposed to cover, I'm supposed to cover some of these. I'm actually supposed to cover more of the diatomic and what would happen when you have not 2 nitrogen molecules, but 2 oxygen molecules, or nitrogen and oxygen, carbon and oxygen, or 2 distinct molecules. What needed to happen? There's actually 2 criteria for a chemical bond to actually exist. Now, you've already done symmetry, so diatomic if you have heterogeneous atom, the necessity condition for a bond is one that they need to have the same symmetry. Orbital, only orbital with same symmetry can bond. Which is basically whether it's actually pointing in the right direction. Or if you want to think about it in physics, which is just momentum, in order for a chemical bond to happen, you lower the energy or you increase the energy. So what it simply means by kind of the symmetry is not the same. If you want to kind of push your ball, like this phone, up that way, I need to put the force upward. So if I were to sweep the force that way, which is not symmetrical, then if I push it this way, then my phone is not going up. That's basically the same thing as a symmetry. Next one here, number 2, is that the energy must be close enough. Must be close. Or relatively close. If you're too far apart, then you either have a complete ionic reaction where the electrons get sucked up or down to one orbital or the other. But more or less, in order to actually share an electron, their energy must be kind of the same. Yeah.
Is it like a sort of quantitative measure of relatively close? How would you describe that?
They're close within 10-ish electron volt from one another. It's usually close enough. You guys use electron volt or no? Yes, okay. 10 volt is close-ish. Once you get to like 40, then you don't have a bond, because that becomes an ionic reaction entirely. Sorry, I think I get something from you? No, okay. So let's do an actual example, which is what I have to cover, probably. That's all right. What I do want to cover is things like HF. So now we have 2 atoms that are slightly different. Then my guess for you is, which one is more electronegative? Hydrogen or fluorine? Fluorine. Fluorine is more electronegative. And which atom binds their electron closer to the nucleus, or just kind of harder to remove? Right, so electron on fluorine, harder to remove. So when we actually look at the orbital diagram and look at exactly where their energy is located, this is where I kind of have to look at the cheat sheet, just because I don't remember these on top of my head. So if you look at hydrogen, then the energy of hydrogen atom is pretty easy. That the s orbital, the ground electronic state, is at negative 13.6 electron volts. Okay. So that's your s orbital. And you have 1 s electrons in the s orbital. But if you have the 2 p orbitals of the f orbital, you'll find that one of them is going to be, there's 3 p orbitals, and they're degenerate. And the energy of these 3 p orbitals are at negative 18.7 electron volt. So they're close-ish, but they're kind of far. In truth, they're actually kind of far apart. This is the difference between these 5 energies, 5 electron volts, right? They're close-ish, but if you look at this is the 2p orbital, this is the 1s orbitals. If you look at the 2s orbitals of the f orbital, which is even buried deeper inside of the fluorine atom, this is actually going to be located at negative 40.17 electron volts. So, 13 versus 40, it's 20-ish or almost 30 difference in energy level. So what happens is that if you have these orbitals, you have the 3p orbitals, and as well as the s orbitals of the f orbitals, as well as the hydrogen atom, the bonding is not going to happen between this and this. It's not going to make that big of a bond. And while they kind of do make a bond, the thing about bonding orbital is that it's not just one-to-one. It actually spreads out. So it's where the symmetry comes in. If you look at the symmetry, 1 s orbitals and s orbital looks kind of spherical, and you can have them overlap nicely. So they can make some tiny bit of a bond, very weak bond, but they can make a bond between the s and the s orbital. But the characteristic is going to be much more closer to the characteristics of the s orbital of your fluorine. So it's from before, if your energy is exactly the same, then you have entirely symmetrical split of energy. But now, your energy is not the same, so the split is uneven. So this is your two s orbitals kind of overlapping with one another. You can also have another one that's similar in symmetry, is you can have an s orbital and a p orbital of the the p orbitals of the fluorine and the s orbitals of the hydrogen can also make a bond. So that's going to happen too, but it's going to get closer. It's going to be lower in energy. As always, whenever you make a bonding orbital, they usually are lower in energy compared to their anti-bonding. So this is going to be lower, but still, it's much closer to the fluorine side in terms of characteristic. It's much closer to the characteristic of fluorine, p orbital. And then you can also have an anti-bonding orbital, but and you have an anti-bonding orbital between the sigma and the p orbital. There. Okay. So we have this sigma. So this is a sigma bond between the s and the p. Anti-bonding orbital, but they're just simply lopsided. Now, whenever you have a diatomic molecule like these two, you can, on occasion, have molecules that, or orbital that doesn't really do anything, right? And we're going to call these ones the non-bonding orbital. I forgot to put one last one in there. So all the electrons that have the same symmetry could combine with one another, but they're not going to be equal. They're going to be mostly F or mostly S or mostly P and so on. They're not going to be the same. Now, so where is these non-bonding orbital? Well, if you kind of redraw the structure and just kind of look at where the energy is located. Oh, actually, let's just fill in the blank first, and let's complete the diagram by filling in the electron first. So I have one electron in the fluorine side of things. Sorry, on the hydrogen side of things. I have one electron here, and I have 7 electrons on fluorine. So the combined molecular orbital, now that we have a lopsided thing, would look more or less like that. 2, 3, 4, 5, 6, 7, 8. There. Right. But the difference is that what I want to emphasize that for one, on occasion you do get non-bonding orbital, and the second one is that on occasions, and the orbital that can bind must have the same symmetry, which is just how they overlap again. Once you kind of recognize how they overlap, which is the p, sigma, and so on, it's easier to see as well where they are. So for example, if I were to draw, I'm trying to show the location of this non-bonding orbital. So we can have a bonding or anti-bonding orbital between the s orbitals and the p orbital of our fluorine and hydrogen. But you can see that there's 2 more p orbitals that are not doing anything. So there's pz is not overlapping nicely with s orbital. So this is a non-bonding orbital, because there's no way for these 2 molecules or orbitals to overlap. They're just not the same symmetry. And if you go and look at the one that's going in and out of the board, it's also a non-bonding orbital. Whatever what you've learned before in terms of the drawing still applies here as well. It's not that big of a difference. So these are the natures of the 2 non-bonding orbitals, and they're mostly your p, z, and p, x orbital, depending on how you define x, y, and z. Let me just kind of finish this off with the linear combination atomic orbital again. So this bond here, we have a bonding orbital between s orbital of hydrogen and s orbital of fluorine. If this is a linear combination orbital theory that we did before, would be s orbitals of hydrogen plus wave function f orbital, s orbital of fluorine. But you see, I want you to notice that this is closer, most like F orbital instead of liking a P. So in fact, if you have two hydrogen, their coefficient before was just 1/2 and 1/2. Now you have a different fractions. You can have, for example, in the fluorine side, because it's much closer to being the nature of the 2s of fluorine, this might be a 9/10. This might be a 1/10. Like 90% fluorine, 10% hydrogen. So the linear combinations of atomic orbital theory could split apart, and essentially you just have one fraction is more than other. So for example, in the anti-bonding orbital, for example, this anti-bonding orbital is closer to the s orbital than it is to the p orbital. You could have, maybe a 60% hydrogen minus 40% sigma p orbital or something like that. So you can have a lopsided distribution instead of a symmetrical one. And I think this is probably where I should close my material. Any questions before I wrap it up? And any questions? Yeah.
So, will it bond at all radial locations?
Sorry, could you repeat that?
Are you showing probabilities of bonding? Is that what that is?
This one?
Yeah.
Characteristics of the actual molecule. It would be 90%. This bonding
So
orbital here.
it would still bond at that area.
Yeah. But the bonding is now smaller than it was before. It's not as tightly bonded.
So it's weaker bonding.
I think not really.
No? Okay.
There's weaker overlap. You see, there's a difference between the intensity of overlap between the bond strength, because what we define as a bond strength is the amount of energy needed to break it apart. So the amount of energy to break it apart is from here all the way there. So the bond energy could be bigger, but they're just 90% is just closer to that, and so on. They're two different things. They're not the same thing. It's just the characteristics of what one bond to the other. And by the way, let me just kind of do this one last one. If you have, for example, lithium and fluorine, it's going to be an entirely ionic molecule. That's because if you look at lithium, this energy is going to be even smaller than 13.6 electron volts. So what happens is that the energy of the fluorine is so much further down. What happens is that this electron just simply falls down. So you get lithium plus and F minus, just because the energy stake is too big. So now you have, in this case, redox reaction, or ionic. You don't have the covalent bond where the electrons actually being shared. Okay, so that's probably where I should wrap it up. Any last minute questions for me? All right, so that's mostly it. Yeah. So when you come back, I think Dr. Provisco will be able to capture that later.